Welcome to Microlecture 28. In this video, I'm going to show you how to define stereocenters as being R or S. Okay, so what we're talking about here is the absolute naming of chirality centers, and there are a set of rules that you need to follow in order to decide whether a stereocenter is R or S. And so the first two rules assign priorities to the substituents as priority 1, 2, 3, and 4. For this rule, priority number 4 is always going to be the lowest priority. So there's going to be 4 groups around a tetrahedral carbon atom, and we're going to be able to prioritize them as being 1, 2, 3, and 4, for example. And that lowest priority group number 4, it should be in the back. Remember, back is dash. All right, so the lowest is in the back. And it is now time to move on to rule number 3. So if the lowest priority group is in the back, then we can think about what it means to kind of rotate from the group that is numbered 1 to the group that is numbered 2 to the group that is numbered 3. Okay? And if we do that without picking up our pencil, going from 1 to 2 to 3, okay, we follow that direction. It is a counterclockwise direction. That means this is an S stereocenter. Okay, so whenever we can move from group 1 to 2 to 3 in a counterclockwise direction with the lowest priority group pointed back, this is an S stereocenter. Let's think about if the groups were prioritized differently. Let's think about this situation here. So in this case, the lowest priority group is not in the back. What you're going to want to be able to do is manipulate the molecule, so turn it in 3-dimensional space, maybe a horizontal flip. Again, this does not require making or breaking bonds, so we're not forming a stereoisomer of this compound at all. We're just showing you what it means to get the lowest priority group into the back. So if I rotate this molecule around a central axis, then 2 is going to be where 1 was, 1 is going to be where 2 was, okay? And 4 ends up in the back, where we want it. And so now we can go ahead and prioritize our groups. In this simple, very simple example, I've already prioritized the groups for you. And so 1 to 2 to 3 is now, if you see, in a clockwise direction. We're going clockwise, so this is an R stereocenter. Okay, so counterclockwise is S, and clockwise is R. Right, what we need to be able to do is that, but with an actual molecule. And so we're going to have to practice assigning priority to the groups or groups of atoms that are around the stereocenter. So let's use a molecule that we've seen before while looking at these chiral compounds. We were thinking about this molecule with the fluorine, chlorine, and bromine on the chiral carbon. And so the rule is to number or prioritize your groups based on atomic number, right? So which atom has the higher atomic number, that's going to be the higher priority. So let's go ahead and prioritize. Fluorine has the smallest. Okay, so it goes fluorine, chlorine, bromine. Bromine has the largest atomic number, so that's going to be priority 1. chlorine is the next largest, and fluorine is the smallest of the group. Not including hydrogen, which of course is the lowest priority group, priority number 4. We just make sure that lowest is in the back, and it is. Okay, and so we can continue with the process of rotating from group 1 to 2 to 3, and we see that this would be a clockwise direction, and this is an R stereocenter. Right, so not all molecules are going to have different atoms at the first atom off of the stereocenter. So sometimes, like in this case, the first atom off of the stereocenter is going to be carbon. So let's do another example that we have seen before. All right, and so we are ranking the groups off of the stereocenter. By atomic number, the first group off of the stereocenter that has the largest atomic number is going to be the OH group, with oxygen having a larger atomic number than carbon. And then we get to 2 carbons. And so here's where we have to use the tiebreaker rule. Use the next atom adjacent to that one in the structure, okay? And so what you can do at first while doing these problems is kind of rank out in order of highest to lowest what you see for atoms off of the dotted atom, that is the atom that's attached to the stereocenter, right? So the highest atomic number that I see coming off of that carbon is this carbon right here, all right? So it's a carbon atom. But then I see a hydrogen and a hydrogen. And so if I were ranking them, I would have, move my carbon atom over here so I can rank below it, hydrogen and hydrogen. So you can rank the 3 things that are coming off of that first carbon atom, highest to lowest atomic number, and sort of see who wins, the carbon on the right-hand side or the carbon on the left-hand side. So we just looked at the carbon on the right-hand side. Now let's look at this carbon on the left-hand side of the stereocenter, and all 3 of the atoms attached to that carbon are hydrogens. So if I were to rank the atoms coming off of that carbon, so silly to rank them, they're all hydrogens. So the carbon wins. Okay, carbon beats hydrogen. And so for that reason, the second priority group is this ethyl, and then the methyl. It's kind of intuitive that an ethyl is larger than a methyl, but this is the systematic way of doing it so that if it's not just a simple alkyl chain, and it's part of a larger, more complicated structure, you have a set of rules to help you determine which group is larger than the next. So if I go from 1 to 2 to 3 in this case, knowing that my lowest priority group is in the back where I want it, I'm going in a clockwise direction. This is also an R stereocenter. Right, and then the last thing to know is that we want to treat double bonds as if they're bonds to the very same atom. So if for example, one of my substituents had a carbon-oxygen double bond on it, okay? And let's say this group is going out, my hydrogen atom is going into the plane. Then the means by which we would determine our rankings would include kind of ranking the atoms off of this carbon. So what I see off of that carbon is an oxygen, and then an oxygen, and then a carbon, okay? So it's as if the carbon-oxygen double bond was actually 2 different separate bonds to oxygen atoms, right? That's kind of just the thought process for what atoms that carbon is attached to. And so what I would get is a priority 1 group here, and then ethyl is larger than methyl as we had determined in the previous example. So 1 to 2 to 3 in this case is a clockwise direction, and we have another R stereocenter. The last little bit here is going to be incorporating R and S into the naming of a molecule. So we can do this with some pretty simple molecules like 2-chloropentane. Let me draw 2-chloropentane. 1, 2, 3, 4, 5 carbon atoms, and on carbon number 2, let's have a chlorine. I'm going to have my chlorine pointed out at you and the hydrogen pointed back, and we'll practice including R or S in the name. So chlorine is priority 1, the longer chain is priority 2, and the methyl group is priority 3. So 1 to 2 to 3 goes in a clockwise direction. This is an R stereocenter, and when we include that in the naming, what we do is put that in parentheses, put a dash, and then 2-chloropentane. So the R or the S designation goes before the name in parentheses with a dash.